excess. Refresh my memory. The limiting reactant is the one that you run out of. The excess is the one you have left over. So when you are doing a factor label in a problem that where you're looking for percent, or where you're looking for limiting reactants, you're comparing what to what? Yeah, your factor label is going to always compare reactants, so you should never see a product in that factor label. Okay, so we're going to go ahead and we'll go right back to our thermite reaction. We'll run it and use the sentence that I just gave you to figure out what those numbers mean. All right, so there's our thermite reaction. Powdered aluminum plus powdered iron 3 oxide yields aluminum oxide and iron. And of course I should put in that symbol there because we have to heat these reactants to get them to go. We talked about that. We typically use a magnesium fuse because that burns at like 3,000 degrees Fahrenheit. Pretty hot stuff. Okay, if you get... Okay, so given 4 moles of each reactant, and this is always the question, this is always the way it's asked. Which is your limiting? Which is your excess? How much remains? That's what you want to know. So we said it's going to be a factor label that compares the two. This is super simple. It's a single step factor label. What do we start with? Given. We have 2 givens. What do we start with? Well, we can only start with one thing though. What do we start our factor label with? It doesn't matter. We can use either of them. So we can start with 4 moles of aluminum. We can start with 4 moles of iron 3 oxide. It doesn't matter. We just have to start with one of the reactants. Okay, so I'm just going to go ahead and start with aluminum. It's the first one in the equation, first one listed. Doesn't matter anyway. We're already in moles, so we can go straight to the heart of the problem. And our mole ratio is going to come right from the coefficients. So we get 1 mole of iron 3 oxide for every 2 moles of aluminum, which means that 4 moles of aluminum can react 2 moles of Fe2O3. So we've got a number. That's great. Does that tell us what we need to know? So you've got this sentence, and you're going to get really good at writing this sentence, and it feels awkward and clunky and stupid, and you think, I don't have to do this, and that's fine. You don't have to do it forever. I don't have to do it forever, but when we start doing limiting and excess, I still have to do it. I've been doing chemistry a lot longer than you. Until you get warmed up and your brain automatically looks at it and goes, oh, that's my limiting. You just start with this. So, number blank could react blank, however we have blank, therefore we will either A, run out of blank, or have blank left over. Oh, that's a lot of blanks. So, that first blank is whatever chemical, the amount and the chemical that you started the factor label with. In our case, we're going to put in 4 moles of aluminum because that's what we started our factor label with. Number 2, and it's cut off on the screen, but it's on your sheet, is the answer for the factor label, the amount and the chemical that you got as an answer. So for us, we're going to say 2 moles Fe2O3. However, there's always a however. And blank number 3 is the chemical that you named in number 2, but this time with the amount that you were given in the problem. So we're looking in space number 3 for iron 3 oxide, but we want to know how much we were originally given. So this is 4 moles Fe2O3. So the first part of our sentence just says 4 moles of aluminum could react 2 moles of iron 3 oxide. However, we have 4 moles of iron 2 oxide. Therefore, we will, well, if is space number 2 bigger than number 3? No. So it's not A. Therefore, we will B, 3 minus 2. we will have 2 moles of Fe2O3 left over. This worked out nicely because we found our excess first, which means we're done. We don't have to do another problem. Okay? We know, so which one is the limiting? Yes, I'm sorry. Aluminum is the limiting. Sorry, yes. Which one's our excess? I was doing the same thing, yeah. Iron 3 oxide is our excess. We have leftover iron 3 oxide. So if we answer our questions, limiting, and I'm just going to draw the line, is the aluminum. Excess is our iron 3 oxide. And how much of that excess remains? 2 moles. Okay. These are easy when they're mole to mole. When they're mole to mole, you can kind of just see the answers for yourself. It's pretty straightforward. Do the exact same problem, but I want to model one where we picked the iron oxide to start with. What would happen if we did that? So again, we're doing a factor label. Again, we can start with either of our givens, and we have 4 moles of each. So what would happen if we had started with 4 moles of iron 3 oxide? Well, again, we're already in moles, so we don't have to do any fancy footwork to get to moles. And we know that it'll have to be moles of iron oxide on the bottom, moles of aluminum on the top. It's a 2-to-1 ratio. We get an answer that is 8 moles of aluminum. Slightly different answer. Very different answer. Okay, so we've got our factor label, we've got our sentence, and now we're going to say, well, 4 moles of Fe2O3 could react 8 moles of aluminum. Because whatever goes in number 2 is, of course, the chemical and amount that we got as our answer. However, we have 4 moles of aluminum. So, if the number in space 2 is bigger than 3, we're going to run out of aluminum. We don't have enough aluminum to react all of the iron oxide. How much aluminum is going to, or how much iron oxide is going to be left over? We don't know from this. So if you get, here's the thing, if you happen on your first shot to get, to get an answer in space B, then you're lucky, you're done. You don't have to do a second factor label. If you're unlucky and you start out and you get an answer here and you find your limiting first, you have to do another factor label to figure out what your how much of your excess you have left over. If you find your limiting first, you're immediately going to know this is my limiting, the other one is my excess. But to answer that third part of the question, how much is left over, you have to do another factor label, because it's only when you get this that you're going to know how much is left over. Okay. Mole to mole is pretty easy. Let's do, but we never do them because we don't have mole scales in a chemistry lab. So what we do in the real world is mass to mass problems. So let's do a mass to mass problem, and we're going to continue to use thermite because we've got it, it's balanced, it's there. So I'm going to change that amount, and now I'm going to say that we're being given 500 grams of each reactant. So, clearly, a little bit different. What do we start our factor label with? A given. Does it matter which one? Nope. We can start with either one. Now, this is a totally different problem than the other one. We don't actually know which is the limiting and which is the excess. So I'm just going to go ahead and stick with my usual thing. In the absence of some compelling reason to do otherwise, I start with whatever's first in the equation. So So we're starting with 500 grams of aluminum. We know we can't compare these things until we're comparing moles to moles. That's the heart of a factor label. So we have to get to moles. What units, what chemical go in the bottom of the next space? Grams of aluminum. And what's the number? 26.90. Oh, 98. Okay, sorry. 26.98 grams of aluminum in every 1 mole of aluminum. So that conversion there will get us into moles of aluminum, at which point we can start to talk about our comparison. So units and chemical on the bottom of the next. Somebody from the Old South. Well, let's just put in units and chemical so far. So moles of aluminum. Units and chemical on the top in that same space, Pacific Northwest. What are we comparing aluminum to? Iron oxide. Yes, iron 3 oxide. So here we're going to put moles Fe2O3. Now if we did want to fill in some numbers in there with those moles, where are we going to get the numbers to fill in there? Coefficients. So aluminum is going to get a 2. The iron 3 oxide is going to get a 1. And we're getting those directly from here. Okay. This is the heart of the problem. I'll use my blue again just because I like it. So we've got our little blue heart. There. Okay. Going beyond that, we don't have a number of moles of iron oxide. We have grams of iron oxide. So what do we have to convert that into? Grams of iron oxide. What units, what chemical are going to go in the last space on the bottom? It's got to cancel. Moles of iron oxide. Moles of Fe2O3, iron 3 oxide. And what units and what chemical are going to go on the top? Grams of same, Fe2O3. Now we have to get molar mass of Fe2O3. We're all set up to do our math. Let's get a raw number. Okay, so we get for our raw answer 1,479.798 blah 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 grams of iron 3 oxide. That's good. You can get a number. Everybody can get a number. Now we got to figure out what that number means. So this is where the sentence helps. Okay, so we start off 500 grams of aluminum could react 1,480 grams of iron 3 oxide. However, we have how many grams of iron 3 oxide? What were we given in the problem? Yes, 500. We only have 500 grams of iron 3 oxide. Therefore, do we run out or do we have leftover? Well, if this number in space 2 is greater than 3, we run out of iron 3 oxide. So iron 3 oxide is our limiting. What does this mean for us? It means we're not done because we don't know how much of the aluminum is going to be left over at the end of this process. We know aluminum is the excess, but to figure out how much is going to be left over, what do we have to do? Another stinking factor label. Jeez Louise. Okay, so because we found that aluminum is the excess reactant, we need to know how much aluminum gets left in the, sort of gets left behind when all the iron has reacted. We're going to do another factor label, and this one, so the last one we started with the aluminum, now we're going to start with the 500 grams of Fe2O3. Units in chemical down below in the next space. Grams Fe2O3. And this is where we're getting into moles. So I'm just going to go ahead and look here. Hey, I already added those up. I don't need to add stuff again. So there are 159.70 grams of iron 3 oxide in what quantity? In 1 mole. Because we're working our way, of course, towards our mole ratio. So in 1 mole of Fe2O3. All right, so now, time to get to the heart of the matter. What units, what chemical go on the bottom to cancel? Somebody I have not heard from yet today. Anybody, anybody?
1 mole of Fe2O3.
Well, we're going to put in just units and chemical so far, though you are correct. So moles of Fe2O3. What units, what chemical are going to go on the top? Again, somebody who I have not heard from at all today. Moles of aluminum. Okay, and now we do have to get our coefficients to fill in our mole ratio, and of course you were right, Alexa. This is going to be 1 mole of iron 3 oxide for every 2 moles of aluminum. But don't answer yet. You get these Ginzu knives. We have to go one more step. We have to get to a mass of aluminum. So now we're just going to, of course, go from 1 mole of aluminum is equal to 26.98 grams of aluminum. 26.98 grams of aluminum. And let's get a raw number. Okay, so we get a raw number of 168.94 grams of aluminum, and we're going to write out our sentence. So we're starting with whatever we started our factor label off with, in this case 500.0 grams Fe2O3 could react, and space number 2 is the answer we got. And I'll sig-fig that, it would be 168.9. 168.9 grams of aluminum, but we have a lot more than that. We have 500.0 grams of aluminum. So we're going to have leftover aluminum. The amount we're going to have is the answer, whatever number is in space 3 minus the number in space 2. So 500 minus our 168, and of course don't round numbers till the end. We get 331.1. Whoops, I put that in the wrong space. Jeez Louise Moser. 331.1 grams of aluminum left over. Okay. Now, whoever set up this reaction did a bad job. You wouldn't want to have that much leftover reactant. It's just bad practice. You want to try to look at the stoichiometry of the problem and figure out how much of each you need so that the numbers are pretty close so you don't have a whole bunch of unreacted leftover stuff floating around. But they make for good problems. Lousy lab technique, good practice problems because they're pretty obvious and pretty easy. Okay, I'm going to assign a few more homework problems that have some limiting and excess practice, and we'll continue on this tomorrow, hopefully FIP on Wednesday on limiting and excess.